In this lecture, we're going to start talking about the half-lives of nuclear decay equations. And luckily, half-lives are familiar. We talked about them quite a bit when we talked about kinetics, and we looked at the rate of reactions for chemical reactions. And now we're going to look at the rate for nuclear reactions. And so this is just bringing back our different orders of decay orders of reactions, reaction rates that we learned about when we talked about kinetics. We had 0, first, and second order that we focused on, and we developed rate laws, integrated rate laws, and half-life equations for all of these. So when we talk about nuclear decay equations, we are going to only be looking at first order decay. So our decay rates will all follow a first order behavior, which at least simplifies this quite a bit. And so the equations that we're going to use are going to be this half-life equation and then our integrated rate law. And again, we've had experience with this, and so we're just going to apply that knowledge to this situation. And if it's been a minute, if you review chapter 12 in the OpenStax textbook, that'll give you a refresher on kinetics. So thinking about first order decay. So right off the bat, it's worth noting that nuclear decay reactions, transformations, don't actually change the rate with temperature. And so because there isn't a temperature dependence, this really is not a chemical reaction. This is something different. So we're not really tracking the concentration of our molecules. We won't be able to calculate the temperature dependence of the rate constant at all. And so our rate equation is going to look a little bit different. So really we're looking at a rate of decay is going to be equal to a rate constant that, again, is temperature independent. And then we're going to track the number of radioactive nuclei. That's going to be N. And so this can be either a number of radioactive nuclei, or it can be a rate of like counts per second, something, or minute, a way of measuring nuclear reaction activity. Now, the half-life equation we're going to use for first order reactions is always going to be this T1/2. The half-life is equal to 0.693 divided by that rate constant K. And then we're going to use our, this is the way I kind of like it. So the one that matches our rate law that we're looking at for the number of radioactive particles is right here, where this is our integrated rate law that'll allow us to calculate the amount of time that passed or predict the amount of a material that's still around. And these ends, these can be replaced with rates as well, and rates of nuclear reaction activity is what that would be. And so the speed with which the substance, a radioactive substance, decays is going to depend entirely on that constant. So that the half-life is going to be, if a half-life is shorter, it means that it'll decay faster, essentially. And hopefully that should be intuitive. And that's what this graph is showing. It's just showing that our half-life of 28.8 days for this, for strontium-90, is going to, every 28.8 days, decrease our total concentration by half, creating this logarithmic scale of decay, looking at the number of radioactive nuclei that are still present. So to measure the rate of decay, we can do this in a few ways. We can look at the number of particles, as we said, or we can look at a rate of decay. And so on the left-hand side, we're looking at the decay of radon. And this is showing the number of atoms of our radon 220 that are around, and over time, essentially. And so we still see this logarithmic decay. We can also think about radioactivity, and CPM. What that is counts per minute. So it's really measuring, the counts are going to be the number of radioactive particles or emitted particles that are detected. And so those counts are how many of these little, in this case, let's actually, it doesn't say. So for gold 198, let's say it's beta particles, the number of beta particles detected per minute. And so that's going to be a measure of a rate of activity. And that should decrease as we decrease the number of particles of gold 198 that we have. And so they should be totally proportional. And since we're looking at a comparison between the number of radioactive particles at time 0 and time t, or looking at the rate at time 0 and time t, that ratio between the two should be the same. So we should be able to interchange number of atoms, or we should be able to use rates and still calculate information about how this decays. So here are some common isotopes by way of example that you may or may not be familiar with. One that a lot of people are familiar with is carbon dating. So carbon-14 has a half-life of 5,730 years, and we use it in archaeological dating. It's useful to look at fossils and the carbon-14 content. That amount at time t allows us to calculate when it formed. What was that carbon-14 atom at time 0 when the species was alive? And carbon-14, when you're alive, that carbon is kind of cycling through your body, right? Like you're constantly making new molecules and breaking down others and taking in food, and so you're kind of maintaining an amount of carbon-14 in your body. And when you die and you stop taking in and synthesizing and acting, then you just have a fixed amount of carbon-14 that then begins to decay to smaller concentrations. Another one that's common is cobalt-60. Cobalt-60 has a half-life of 5.3 years, so significantly shorter. And it's actually used in therapy, in cancer treatments. It is a long half-life still for something that you would use for a medical purpose. And so cobalt-60 is often used as a source of gamma radiation or X-rays to target cancer cells therapeutically. Or they also generate beta particles that then generate gamma radiation, which we'll talk about in a bit, or in a few lectures. Iodine-131 is also used in a medical context. It has a much shorter half-life, 8 days, and it is used actually in two ways. It's used both to target and attack cancer or tumor cells in thyroids, but it's also used to image the thyroid. So depending on the concentration that you ingest, if it's a really small amount, it won't do very much damage, and it'll decay quickly away because there's not very much of it. That'll allow you to image the thyroid because it kind of selectively within your body, it takes up iodine. And so if you put in large amounts, then it would collect in the thyroid and then it would damage the cancer cells. Potassium-40 is another one that's used for dating, but it's used for geological dating. And the reason it's geological versus archaeological is because its half-life is 1.3 times 10 to the 9th years. That is a lot. So that's going to allow us to actually look at things that are like, how have these rocks changed over time, rather than just fossils that might be within a 50,000 year time frame. So it allows us to go beyond that. Phosphorus-32 is another one that's used in a medical context. This one is used for leukemia treatment, and it again has a shorter half-life of 14.3 days. Technetium-99 is also used in a medical setting for imaging, and so this is used for diagnostics. And it has a very short half-life. It's 6 hours, which is great. It produces gamma radiation, but it can't do it for very long because it has such a fast half-life. It also has such a fast half-life that we can't make it and ship it to a hospital. So hospitals need to be able, or places where you're doing organ imaging with technetium-99, you will need to actually make it there on site to use it. And then lastly, uranium-235 is another common one a lot of people have heard of. It has a very long half-life as well, 7 times 10 to the 8th years. And it's actually used in nuclear reactors, which we'll talk we'll talk about more in a few lectures. So let's walk through an example of a half-life problem, and then we'll do another example following that. So this is looking at Pu-236, and I've completely forgot what Pu is. It's plutonium. I should have known that. So we've got plutonium-236, and it has an atomic number of 94. It's in the actinide series. So we are told that we have a sample with a mass of 1.35 milligrams. And so this is really telling us the number of radioactive particles. We're quantifying an amount through mass. at time 0. And we want to calculate the mass that will remain after 5 years. So our time is going to be equal to 5 years. And what we want to know is how much of this is around at 5 years. So we're going to need to use 2 different equations for this. We're going to need to use our half-life equation and our integrated rate law. And so our plan here is that to figure out what this N is, or the amount that we'll have after 5 years, we really need to know our initial amount, which we know, great, that's our 1.35. We need to know our time, we know it's 5 years. So the piece that we're missing is our rate constant, which we're going to have to calculate from our half-life. And because we know our half-life is actually 2.86 years. So this will be kind of a 2-step problem. All right, so let's plug in for K. Let's solve. So K is going to equal 0.693, and I'm just rearranging this equation algebraically by our half-life, which will be 2.86 years. So we'll get a value for this that is 0.2423 years, inverse years. All right, now that we have that, we can plug into our integrated rate law, and you can plug into it as I have it written out here. We can also rearrange it to solve for the amount we're going to have at 5 years. So at t equals 5. That'll be equal to our initial amount times e, our exponent to the negative kt. So, and that's just rearranging. And remember, the opposite of a natural log is e. So we have our amount at time 5 years, is going to be equal to that initial amount, which is our 1.35 grams, e to the negative k that we just calculated, 0.2423 years to the negative 1, and times our time, which will be 5 years. And so our units here, the inverse years and years should cancel out, leaving us with an answer that'll be in grams. And so whatever that N initial is, the units will be the units that we get out in our answer. So just plugging this into our calculator, I'm going to get a value that is 0.40 milligrams. It's because I forgot to put the milligrams. Sorry, right here. I had 1.35 milligrams. And I just carried over the grams and not the milli. So I'll end up with 0.4 milligrams, which is significantly less than our 1.35. So try the next problem on your own and then watch the solution to see how it goes.